In this video, we're going over section 10.2, which is about how to perform a hypothesis test regarding a population proportion. So you've seen this before, but these are our steps in a hypothesis test. And step number 3 was to use math, and that was intentionally vague in our last video, but we're going to use math to determine whether or not the evidence we've collected represents sufficient evidence. And so in section 10.2, we're doing this for a hypothesis you might make about a population proportion. Just as a heads up, in 10.3, we're going to be figuring out the math for a hypothesis test about a population mean. So whether you're talking about a population proportion or a population mean, the math is going to change just a little bit between those cases. So step 1, I've made a statement, or I've made a claim, and my claim is that more than half of people with the New Year's resolution are going to give up on their resolution before February. So we need to determine, what are we seeking evidence for? That would be our alternative hypothesis. And we also need to determine, what is the converse of that? That would be our null hypothesis. And for us, what I'm seeking evidence for, I'm trying to support my claim with evidence, right? And so I'm trying to say as my alternative hypothesis that the population proportion is greater than half. Because I've said more than half of people are going to give up before February. Now, the null hypothesis is going to be the converse of the alternative hypothesis. So if my alternative hypothesis is P is greater than half, then my null hypothesis must be that P is less than or equal to half. Now in step 2, we gather data, and let's say after gathering my data, I survey 50 people and 27 of them gave up for February. So I can calculate a sample proportion, which is going to be x over n. In our case, that's 27 over 50, which is going to be 0.54. Now you'll notice that then my sample proportion is greater than 0.5. So that means there is some evidence in favor of my alternative hypothesis. Because if my sample proportion were less than half, there would be no evidence at all towards my alternative hypothesis. But in our case, we do have some evidence. The question, though, is, does this represent enough evidence? Does the results of my survey represent enough evidence where we can conclude with certainty that the population proportion is greater than half? We figured out my sample proportion was greater than half, but the sample proportion is not necessarily the same as the population proportion. So how much certainty do we have that the true population proportion is greater than half? So again, there's my n, my x, my p hat. And step 3 for us, again, doing the math part of this, our goal is to calculate the probability that if the null hypothesis were true, then we could obtain data like ours in our sample. Or just as well would be data that was more extreme than ours, like a sample proportion greater than 0.54, right? Like ours would be p hat equals 0.54, or more extreme than ours would be p hat greater than 0.54. So what is the probability that p hat is greater than or equal to 0.54? That's essentially the question that we're asking. And so, yeah, I think I've pretty much said this. Our goal is to calculate the probability that if exactly half of the population gave up before February, then we could obtain survey results with 27 or more respondents. So what's the probability that p hat is greater than or equal to 0.54 given that the population proportion is exactly half? And so we read that vertical line as the word given, right? So it's the probability of this given this assumption. Now, this has a special name. This probability is what we will often refer to in hypothesis testing as the p-value. So with respect to our example, our p-value is just going to be the probability of that. And once we calculate the p-value, what we're going to do is compare it to this. Remember, lowercase alpha is our level of significance. And we wanted that to be a very small number. If our p-value is greater than alpha, then we don't reject our null hypothesis. But if our p-value is less than alpha, then we reject our null hypothesis. Now, you are going to get to choose your level of significance. If it's okay to have a type 1 error, then we are going to make alpha relatively large, like a tenth or 10%, right? But if it turns out that it's really, really bad to have a type 1 error, then we're going to make alpha a small number, like 1%. Remember what a type 1 error is. A type 1 error is where we say that we conclude in favor of our alternative hypothesis when actually our null hypothesis was true. That would be a type 1 error. For us, typically, we're going to use a type 1 error of 0.05. But in other applications, that might change, right? So, maybe, depending on the decision, if it's okay to have a type 1 error, like I said, you might use 0.1. Or maybe in certain applications, depending on which field you're researching in, maybe if you're doing like a sociology experiment, maybe use 0.01. I know that, in particle physics, for example, if you're a physicist working at like the particle accelerator, the particle collider in France, if you're working at CERN, I think what they typically use for particle physics, if you wanted to demonstrate evidence for a new theory of quantum physics, their level of significance is going to be very, 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 very small. Don't know if that's exactly the level of significance, but it's going to be something very, very tiny, which sort of corresponds to saying that it would be bad to make a type 1 error. It would be bad to accept a new model of physics if it weren't actually true or more accurate than the old model. Now, 1 minus alpha times 100%, that represents a minimum level of confidence. And so if your level of significance alpha is 0.05, this would correspond to a 95% minimum level of confidence. If you had an alpha of 0.1, that would correspond to a 90% minimum level of confidence. And 0.01 would correspond to a 99% level of confidence. And this, I'm probably going to butcher this math because there's so many zeros, but it would correspond to like a 99.1, 2, 3, 4, 5, 6, I think that's 7. It would correspond to a very, very high level of confidence, right? By the way, this may remind you of doing confidence intervals, and we had to decide if we were going to make a 99% confidence interval or a 95% confidence interval or a 90% confidence interval, and then we calculated alpha. Remember, We calculated alpha by deciding we would have, let's say, a 95% confidence interval, and we set it equal to 1 minus alpha times 100%, and then we calculated alpha then to be 0.05. This alpha has the same relationship with the minimum level of confidence, right? So our level of significance and our minimal level of confidence has the familiar relationship. So it's okay to associate those two in your head. And just a quick reminder from section 10.1 and the vocabulary we were using. If we say we do not reject the null hypothesis, this means we did not find enough evidence in favor of our alternative hypothesis. But if we choose to reject the null hypothesis, that means we did find enough evidence in favor of the alternative hypothesis. How do you calculate this p-value that we're so interested in? First, let's ask the question, what would the standard deviation of the distribution of the sample proportion be if the null hypothesis was correct? And so what was our null hypothesis in my example? Well, our null hypothesis was that p is less than or equal to 0.5. We're going to come up with this little value p subscript 0. So that represents what the population proportion would be at the boundary of my null hypothesis. And so this is going to be 0.5. I'm going to say p naught is 0.5 because my null hypothesis, the boundary between my null hypothesis and my alternative hypothesis is p equals 0.5. Hopefully you see how we came across this value. So using p naught equals 0.5, we're going to come back here, and with p naught equals 0.5, all I need to do to calculate this sort of standard deviation value that I'm going to call s subscript p hat, and this not just represents that it's standing in place for the null hypothesis. Well, this would be square root of 0.5 times, 1 minus 0.5 is just 0.5 divided by n. And in my example, I surveyed 50 people, so my sample size would be 50. So what's the square root of 0.25 divided by 50? Let me pull up a calculator really quick. Square root of 0.25 divided by 50. And that would be 0.0707. Okay. Then, once we have this value, we've answered the question, what would the standard deviation of the distribution of the sample proportion be if the null hypothesis was correct? We're going to calculate what we call the test statistic. So we'll use Z naught for this test statistic. And so remember this value on the previous page, we calculated this to be 0.0707. And in the numerator, we're going to do p hat minus p naught. And remember again that p naught was just the boundary between the null hypothesis and the alternative hypothesis. So that was 0.5. So for us, Z naught is going to be p hat, which is 0.54, minus 0.5 divided by 0.0707. So this is going to be 0.04 divided by 0.0707. So something a little bit more than half. .566. And then there's still more steps here. We're finally ready to compute the p-value. And below, whenever we use this CDF, that CDF refers to the cumulative distribution function of the standard normal distribution. And so we have three different cases that you'll notice. And there's three different types of hypothesis tests we might see. Either your alternative hypothesis is that your population proportion is greater than some value, or your alternative hypothesis could be that your population proportion is less than some value. Or in the third case, in green over here, we could make the alternative hypothesis that p is just not equal to some specific value. So in the first case, where p is greater than some value in our alternative hypothesis, I think we would call this a right-tailed test, because we're interested in, our population proportion being greater than some value. So in the distribution of sample proportions, we're looking for this area, this probability that our true population proportion is greater than some specific value p naught. In this case, here in the middle, this would be like a left-tailed test, because we are looking for, the probability that p, my population proportion, is actually less than some value p naught. And then here, where I just say p is not equal to p naught, this is what we're going to call a two-tailed test, because we're going to have some value p naught, and we're going to be asking what is the probability that my actual population proportion is less than or greater than p naught. And so we're going to calculate some area that falls just a little bit outside of p naught under the distribution. So anyways, we have different formulas for the p-value depending on which this is. And you notice for the right-tailed test, since we're calculating the area on the right side under a distribution, we're talking about 1 minus the standard normal distribution evaluated at that z0 test statistic that we just did, which was 0.566. If we're doing a left-tailed test, this is just the CDF evaluated at 0.566, and if we're doing a two-tailed test, notice these are absolute value symbol. So this would be 2 times the standard normal distribution CDF evaluated at, well, first take the absolute value. So if instead of 0.566 you had a negative number, take the absolute value, make it positive, but then take the negative of it, right? And so we'd be taking the CDF of negative 0.566 in this case. Whatever you take the CDF of in the two-tailed test, you should always be taking the CDF of a negative number, and then multiplying it by 2, because this is a two-tailed test. Okay, so for us, we are talking about a right-tailed test, and so we're going to do this. We're going to do 1 minus the CDF for the standard normal distribution evaluated at 0.566. And that's going to be a p-value of 0.286. Okay. One last thing I'll say, and don't let this confuse you. What I mean by that is, if this is confusing, just ignore it. But the standard normal distribution, this is symmetric. And so instead of calculating 1 minus the CDF here, it would actually be okay as well to just calculate CDF of the negative absolute value of z0, and that will give you the same thing. So instead of doing 1 minus the CDF of 0.566, what if instead I just calculate the plain old normal CDF at negative 0.566? And notice I get the same value as I would with the 1 minus the normal CDF. So that's just saying that this distribution is symmetric about the mean, and so some area like this on the left would be the same as some area like this on the right. That's just as far away from the mean. So both of those formulas are correct. Both of them are going to work. Yeah. In any case, what does this p-value mean? So we calculated 0.286 in my example. So let's remind ourselves of that. What does that mean? So whenever we do 1 minus our p-value, so 1 minus 0.286 would be 0.714. And then I multiply by 100%. That would be 71.4%. This represents our percent confidence that we have in favor of our alternative hypothesis. And so based on my data, I'm going to scroll way back up in my slides. Based on what I've gathered data-wise, when I surveyed 50 people and 27 of them told me they gave up on their New Year's resolution before February, that survey data, with its just a little bit of evidence that it offers in favor of my alternative hypothesis, that survey data gives me 71.4% confidence that the population proportion is greater than half. It gives me 71.4% confidence in my alternative hypothesis. In other words, there would only be a 28.6% probability that we would be committing a type 1 error. There's only a 28.6 probability that we would be wrong to reject the null hypothesis. But that's actually a pretty big percentage, and you wouldn't want to publish something in a journal if there's a 28.6% chance that you're wrong. And so usually you choose a level of significance to be much smaller than that. So that way your p-value has to be much greater. So that's the way, your confidence has to be higher before you publish something. You don't want to publish something that might be wrong. But this is a very good interpretation of the p-value. And I personally find it very neat that given some survey data, we can actually calculate an exact degree of confidence that we have in our hypothesis. We don't just have to go by gut feel. We don't have to just look at our survey data and tell us how we feel about that and how much confidence it makes us feel like we have. But there's actually math out here that is not terrible to calculate, where you can calculate an exact degree of confidence. And this would be important even if you were just in business. Like suppose you don't go into any of the sciences, you don't become a biologist or a psychologist or a physicist and so on. What if you just go into business? Well, when you're making business decisions, you want to have an exact degree of confidence in things like what is the demand out here? What does the market look like for a certain product that I'm about to sell or a certain service that I'm about to go into business with? Another way that you could perform a hypothesis test, rather than going through this process of calculating the p-value and comparing that to a chosen level of significance, instead of doing that, you could construct a confidence interval. So we actually learned how to construct a confidence interval about the population proportion in section 9.1. So do that first. Step 1 is make the confidence interval. And then step 2 is we ask ourselves this question. Does my hypothesis cutoff, that p-naught value, remember in our example, the p-naught is just the boundary between the null hypothesis and the alternative hypothesis, and so in that case it was 0.5. We ask ourselves, does that boundary between the null and the alternative, does p-naught fall within the confidence interval that we've just developed? If yes, if p-naught falls inside of our confidence interval that we just built, then we cannot reject the null hypothesis. If no, it doesn't fall inside the confidence interval, then we may reject the null hypothesis. So the benefit to doing a hypothesis test using a confidence interval is that after you've performed the hypothesis test, you also have the confidence interval for free. And so that's really nice. The benefit of doing a hypothesis test with a p-value is that after the hypothesis test, after we say yes or no, we also happen to know the exact percent confidence that we have in favor of our hypothesis. And so there's a benefit to doing it both ways. And honestly, if I were a statistician actually looking at a problem very closely, I would perform my hypothesis test both ways. I would build the confidence interval and calculate the p-value so that I would both have the confidence interval and have my exact percentage confidence. And then I would have two different ways as sort of a check on my work to answer yes or no to the hypothesis test question. And these two ways of conducting the hypothesis test will always give you the same answer. It should always give you the same yes or the same no when it comes to rejecting the null hypothesis. And if they don't, if one of these methods tells you to reject the null, the other method tells you that you cannot reject the null, that means you've done your work incorrectly and you need to go back and probably retry both methods. This is the last slide in the deck, and I just want to show you a certain shortcut on the TI-84. And the shortcut is that we could go to the button Stat and then highlight Tests, and then go select number 5, which says 1 proportion z-test. So PROP stands for proportion. We're talking about a hypothesis test about a population proportion. And it's called the z-test because we're going to use the standard normal distribution, remember, to calculate my p-value from my test statistic. That's why it's a 1 prop z-test. So we pick number 5, where it says p0. Remember, that's the cutoff between my null and my alternative hypothesis. X, well, we sampled a group of 50 people, and 27 of them told us that they gave up on their New Year's resolution already. N is the number we sampled. We sampled 50 people. What about my type of hypothesis test? Remember, it falls into one of 3 categories. Either it's a right-tailed, left-tailed, or two-tailed. In our case, we were doing a right-tailed test, so we were hypothesizing that our population proportion was greater than p0. And so here, I'm going to choose the option that says greater than p0 and highlight that and select it. There's 2 options down here. One says calculate, one says draw. I like to choose draw on my first go around, and so I click enter. And it's going to draw me this nice bell curve, which would be the standard normal distribution. And it's going to highlight in blue the area which represents the probability of making a type 1 error. In other words, that area highlighted in blue, that is my p-value of 0.286. Also, on the bottom of the screen, it tells me my z-value, which is my test statistic, which was 0.566, right? Right here. And on the bottom of the screen, it also tells me my p-value. So if I do 1 minus my p-value, that tells me my percent confidence. So your percent confidence is represented by the unshaded region under this curve on your calculator. That's nice. Let's go back to stat and then go over to tests again and then just choose 5. And now we'll scroll down and keep the same data, but we'll choose calculate instead of draw just to see what that shows us. And again, it shows us our test statistic, 0.566. It tells us our p-value, 0.286. And this time it tells us our sample proportion, which was 0.54 in our sample size. So it doesn't actually give us a whole lot more information here. Really, the only additional thing it says is our sample proportion. So you can probably just do the draw option if you need to on a test. So that about sums it up for hypothesis tests about a population proportion. Sort of what it is and what the shortcut is that you might want to use on your exam. Of course, let me know if you have any questions about this. And I'll see you again in our video on 10.3.